This video is brought to you by mywayteaching.com.
In this particular part, we are going to study about blood flow and heart attack. Bernoulli's principle helps in explaining blood flow in artery. So the artery may get constricted due to the accumulation of plaque on its inner walls. Okay. So in order to drive that blood through this constriction, a greater demand is placed on the activity of the heart. So the speed of the blood flow in this particular region is raised, which lowers the pressure inside and artery may collapse due to the external pressure. So the heart exerts further pressure to open this artery and forces the blood through. As the blood rushes through that opening, the internal pressure once again drops due to the same reasons, which leading to a repeat collapse. So this may result in heart attack. Okay, the artery it may get constricted due to the accumulation of plaque on its inner wall. So if we try to drive the blood through these constriction, a greater demand is placed on the activity of the heart, and even that pressure will be raised. Okay, the speed of the flow of the blood in this region is raised, which lowers the pressure inside, and artery may collapse due to that external pressure. Okay, if it heart exerts further pressure again, it will result in the repeat collapse, which may result in heart attack. So now let us study about dynamic lift. This dynamic lift is the force that acts on a body, such as airplane wing, a hydrofoil, or a spinning ball, by virtue of its motion through a fluid. Okay, it is the force which acts on a body. Example, airplane wing you can take, or a hydrofoil, or a spinning ball by virtue of its motion through a fluid. So in any, many of the games such as cricket, tennis, baseball, or golf, we notice that a spinning ball deviates from its parabolic trajectory as it moves through the air, isn't it? So that deviation can be partly explained on the basis of Bernoulli's principle. So you just consider the first case where fluid streaming past a static sphere, which means ball moving without spin. The first case is ball moving without spin. So this figure it is shows an example. Okay, it shows the streamlines around a non-spinning ball moving relative to a fluid. From the symmetry of streamlines, it is clear that the velocity of fluid, which means in this particular example, the velocity of air above and below the ball at corresponding points is the same, resulting in zero pressure difference. Okay, so the air therefore exerts no upward or downward force on the wall. You can see from this figure there is no upward or downward force on the ball from the air. So this is an example of ball moving without spin. Okay. Now considering the second case, ball moving with a spin. So in this example, a ball which is spinning drags air along with it, isn't it? So if the surface is rough, more air will be dragged. And this figure, it shows the streamlines of air for a ball which is moving and spinning at the same time. It is moving as well as spinning. So the ball is moving forward and relative to it, the air is moving backwards. So the ball moves forward, but that air moves backwards. Okay. Therefore, the velocity of air above the ball relative to it is larger and below it is smaller. Okay. So because of this, you can see here the streamlines are crowded here above and they are ratified below. Okay, this difference in the velocities of air results in the pressure difference between the lower and upper phases, and there is a net upward force. In the first case there was no upward or downward force, but here there is a net upward force, isn't it? On the ball. So the dynamic lift due to spinning is called as Magnus effect. We call the dynamic lift due to spinning as Magnus effect. Okay. And if you consider the third case, that is aerofoil or lift on aircraft wing. Aerofoil or lift on aircraft wing. So this is the third case. So in this figure, it shows an aerofoil or we can say aerofoil. Okay, aerofoil. It is aerofoil or lift on aircraft wing. So it shows an aerofoil which is a solid piece shaped to provide an upward dynamic lift when it moves horizontally through air. So it provides the upward dynamic lift, and the cross section of the wings of the aeroplane looks somewhat like the aerofoil which is shown here. The cross section of the aeroplane wing, it looks somewhat like this only, right? Isn't it? Yes, with the streamlines around it. When aerofoil moves against the wind, the orientation of the wing relative to flow direction causes the streamlines to crowd together above the wing. See here, you can see the wings are crowded together above the wing more than those below the wing. Isn't it? You can observe it from this figure. The flow speed on top is higher than below it. Okay, the flow speed on top is higher than below it. Okay, and there is an upward force resulting in a dynamic lift of the wings, and this balances the weight of the plane. Okay, upward force will be there, which resulting in the dynamic lift of the wings, and it balances the weight of the plane. Okay, So this is the air flowing past an aerofoil. So these three are the different cases: when ball is moving without spin, when ball is moving with spin, and when we are considering an aerofoil or lift on aircraft wing. Okay. Now let us see a very simple problem to understand this. The problem is a fully